All right, it's about the time. Tianjin, shall we get started, or you will want to wait for a few more minutes?
If you want, we can wait for a few minutes.
Okay,
Good.
Let's wait for 2 more minutes.
Thanks.
Shall we start, Tianjin?
Sure.
Okay, so good morning, everyone, or good evening, depending on which side of the globe you are at. So welcome to the last day of SUSY 2021. So my name is Hao Han from the University of Pittsburgh, convene this wonderful section here. So this morning, for the first section, we will have 3 speakers. Without any overdue, let's get started. So the first speaker is Professor Renata Kalos from the Stanford University, and her talk is going to be string inflation. Renata, please go ahead to share your screen.
Hi, everybody. I'd like to express my gratitude to organizers who asked me to give this talk about string inflation. And I'll tell you what I know about the period from 2013 to 2019, where we got data from BICEP Keck 15 and Planck. Then there was just recently, a couple of weeks ago, CMBS4 collaboration meeting. There were certain news there in particular that BICEP Keck 18 might be released soon. We don't know when. And then I'll tell you about the future missions, which are expected to give us something new around 28, 29. My personal agenda was slightly more broad than the title of my talk. And the issue I was interested and remain interested in is what can theoretical physics in general say with regard to cosmological data on inflation. And everybody have seen these pictures, and we all know that there are thousands and thousands of correlators which gave us these beautiful pictures. And after Planck, there were many other experiments which are in good agreement with regard to early universe. In addition to Planck, we had the WMAP ACT SPT, ACT POL, Polar Bear, BICEP Keck, and more coming. So what can we say as of today? And because the title of the talk I was asked to give is about inflation in string theory, I'll start with the reminder that there is a textbook by Bauman and McAllister from 2015, which tells us that string theory is a complicated object which has many different related theories, including M theory, type 2A, type 2B, and others. And the most important thing about the fact that string theory has UV completion is different from other theories which we know, is that at the worldsheet, it is a two-dimensional quantum field theory, and therefore it is consistent and UV complete. However, when we want to explain the observation around us, we have to go away from the worldsheet to space-time, and things become more complicated there. So soon after Planck 2013, there was a review by Burgess, Kikoli, and Kiveda about the status of models versus data. There were lectures, TASI lectures of Silverstein in 16. And then later on, after Planck 2018, I had a review paper with Andrei Linde about CMB targets after Planck 2018. And so many people viewed string theory concerning the relation to cosmological data in the limit of supergravity associated with critical superstring theory. And therefore, this is 10-dimensional supergravity with local sources like D-branes and O-planes. And then we still have to do the compactification to D equals 4 to explain the observations, because the world we see now is nicely described by 4-dimensional theory. And so there are a number of interesting cosmology supergravity talks at this conference by Xu, Antoniadis, Terada, and Sorba, and they all have kind of relation to supersymmetry, supergravity version of cosmology. On the other hand, string cosmology can be studied without supersymmetry. And this is the situation when you use non-critical string theory, where D minus 10 is not 0. And that was discussed in the talk by Silverstein the first day. Now, let me shortly describe for you the table, which was in 2013, where Burgess et al. Made a list of various known at that time string inflation scenario. Then they put the two observables which we have in CMB, tilt of spectrum and level of gravitational waves. And so here we have the list of NS, and here we have the list of R. And most models after Planck 2013 either were ruled out by the value of NS, or we learned that they have very small value of R, and therefore they will not be tested soon. And so the only models which survived Planck 2013 definitely are axion monodromy, and they are testable soon, and fiber inflation. And other models are not either already ruled out by the value of NS, or they have too small R. And so for the next 20 years, there is not much expectation that we will know something about them. And more recently, there was the paper where the bound on R now was announced to be 0. Oh, sorry, there is a missing 0 here, 0.044 at 95% confidence level. I'll tell more about it. So I had a slide in 2018, approximately, when this slide shows you that this is what we knew in 2010 about R and NS. There was a huge area where many models were known, but then by 2018 and $1 billion spent, this blue area become only area where we expect models to be consistent with data. And so many models just were gone. Some of them, however, survived. And I'll focus on the models which remain interesting and testable either soon or say next 10 years from now. So to explain inflation, it is extremely useful to have theory with shift symmetry. The most famous example of shift symmetry is the axion potential, which leads to either natural inflation scenario or axion monodromy scenario. And these mechanisms do not require supersymmetry. The other possibility, which was used more recently, is the situation where there is Goldstone shift symmetry of supersymmetric flat direction in supergravity. And then we have uplift of this flat direction to plateau inflationary potential. And these are Saxion flat directions. They are partners of axions. And what we learned that when there is a nilpotent multiplet, a chiral multiplet with special properties, then we can build such model in string theory inspired supergravity. In particular, those models are rather well known by now, and they're called alpha attractors. But let me also notice that fiber inflation, Higgs and R-square inflation, the inflaton is a scalar rather than pseudoscalar. It all became clear when the first understanding of how to build inflation in supergravity from 2000 by Kawasaki, Yamaguchi, and Yanagida, and they have realized that once they add an additional multiplet, which is supposed to be heavy, this makes a tool for model building. And now it is even more clear that once you have this nilpotent chiral multiplet, which represents Volkov-Akulov non-linearly realized supersymmetry, which also correspond to anti-D3 brane in string theory, it is a powerful tool in cosmological model building, which we used both for dark energy as well as inflation. And so here is the picture from 2018. Probably many people have seen it. Phi squared was gone. The simplest and nicest model was ruled out by the value of R. And then phi squared could go to the model known from 1990, natural inflation, but it goes too far to the left. And then axion monodromy goes slightly to the right. And at that time, in 2013, we suggested this model, which is known as alpha attractors, and it just moves phi squared in the sweet spot of Planck data, where also we have from very long time ago Higgs and Starobinsky inflation. They are here. So this is the interesting slide of Eva Silverstein from Strings 2021, where she observed that to move phi squared in this direction requires this idea of flattening, which is what axion monodromy did, but also because it tends to be outside of a sweet spot for NS, there is a mechanism of multi-field which pushes it back in this direction. And very recently, there were ideas known as double monodromy inflation. And these people observed that if you add a second stage of monodromy, so that the actual number of e-folding in the first stage is smaller, then you can also push the value of NS inside instead of being outside. So these two stages are such that first the field goes in the gutter and then moves in this direction. So what has been achieved here is close to what I showed you in the slide of Silverstein, but it's just a different mechanism. The fact is, the claim of this group is that you can produce models where R is between O2 and O6, and the price for this is to go from these monomial models inside here by making second stage. So the first stage of inflation has just 30 or 40 e-foldings. However, the models which actually works are here, and they have somewhat strange potential, I would say, 5 to the power 1 over 10, 5 to the power 1 over 4. And those are not the ones which have clear microscopic string theory models under this potential. So it is not quite clear what will happen. And basically, we need more data. There was another attempt, one of them very recent, to study aligned natural inflation in string theory by these people. And so what they did, they involved Kim-Nielsen-Pelosi alignment mechanism, as well as various tools of string theory. And they end up with this set of models. And as you see, this is a plot of spectral index and tensor to scalar ratio, which you see here. But in the end of the day, you can see there was a significant effort, but all models are still far from the sweet spot of data. They are not in the blue area. So let me then switch to Planck constraints on tensor to scalar ratio, the recent one. So certain group of people used the most recent Planck, and the conclusion was that Planck, without anything else, the constraint on R is 0.056, and when they added bicep Keck 2015, it became less than 0.44. And this is claimed to be tightest limit on R today. And this is the interesting slide from CMBS4 summer collaboration, where it is like certainly true that the predictions of inflation are checked, and we're looking forward to know more about these tensor perturbations. So why it is important to hunt for primordial gravitational waves? Because if we detect them, it would mean that we probe the energy at scales unreachable by particle colliders. And so it was also explained that why 2028-29 are important, because this is where the major CMB instruments will be start working. LightBird, the satellite mission, and CMBS4 LSST ground mission, and they appear to be extremely complementary. And therefore, at that time, we expect some new data. And so the recent work, which I explained in superiority section, my work with Linda, Yamada, and Raza, was to ask which model of inflation will fit the data and what we will learn about fundamental physics, and I'll move on. So this was from Flagger talk, and what you see here is he expects that monomial models like phi to the power 1 or 2/3 are about to be excluded, and big bicep Keck 18 maps about to be released. This is the plot where what we will expect for R between 10 to the minus 2 and 10 to the minus 3. And the particular model, which are special class of alpha attractor Poincare disks, which I plan to explain a little bit more. And so the targets involve, of course, R squared and Higgs, which are here. But in addition, there are these 7 lines, which you see. They're discrete alpha attractor models. And the meaning of the alpha is that it is scalar space curvature. Or in terms of Escher pictures, 3 alpha is the radius square of the Escher disk, and cases where we have 3 alpha discrete between 1 and 7 just happen to give R between 10 to the minus 2 and 10 to the minus 3, which is precisely where the satellite mission plans to get data. And so this is benchmarks for T models. They're actually very simple. T models are just tanh squared, and they give this whole yellow band in addition to discrete targets. And for E models, we have 1 minus E square root of 2 to 3 alpha phi, and everybody knows that with alpha equals 1, this is Starobinsky model, but we have these more general models. And so the new idea about sequestered inflation, which we just came up with, that we can construct supergravity, which allow one to sequester phenomenology of inflation from Planckian energy scale physics, which can be associated with string theory or M theory. At step 1, we found a very interesting situation that we have W superpotential flux superpotential in string theory and M theory, which have interesting new symmetries, which lead to Goldstone supermultiplets. And at step 2, we uplift this to Plato inflationary potentials. And the technical tools which we are using are Goldstone multiplet and symmetries of flux potential and nilpotent multiplet. And I'll just quickly remind you that the whole story of KKLT uplift can be understood either using anti-D3 brane or Volkov-Akulov nonlinear supersymmetry, which is equivalent to just a statement that one of our multiplets is nilpotent, such that the scalar is a bilinear of a Goldstino fermions and not a fundamental field. If this is one of our tools, we can build models which are consistent with the data now, and they will be tested in the future data. So this is stringy origin of Plato potentials, kind of a picture which we came up with. At step 1, we have Goldstone multiplet, the red line here, and 1 is a M Planck equals 1 scale. And at step 2, we have a Plato. So if you look at this picture and you plot your potential, this is what you see. But if you make a magnifying glass and you look, you remember that experimentally H squared inflationary is of the order 10 to the minus 9 of Planck, then what you see, you just zoom in this area and you see that the Plato potential here remain Plato, but here they have a nice exit into de Sitter with positive cosmological constants. So these potentials appear to explain the origin of Plato potential via stringy flux superpotentials. And so this is the—
Renata, 5 more minutes.
Five
more minutes.
Yeah, very good. I am about to finish. Very good, thank you.
Thank you.
So the formula for NS for these models depends only on number of e-folding. This is why you see these lines. Whereas the formula for R depends on 3 alpha significantly. And so the options which we have is the discrete set of values, 3 alpha equals 1, where n is integer, and it just happened to be between 1 and 7. And it is motivated by maximal supersymmetry, and it is compatible with the data. Therefore, we can say that maximal supersymmetry, M theory and string theory, which could be viewed as 11 or 10-dimensional supergravity plus local sources, D brane and O planes. And this is the case when we have discrete targets. On the other hand, if we have minimal supersymmetry, and then we have continuous set of values of 3 alpha, and this is just 4-dimensional supergravity. And again, as of today, they all agree with the data. But the future data will certainly tell us more. And so to conclude, minimal supersymmetry n equals 1 supergravity prediction. There is a continuous band. Any R is possible, and S already fits the data. This formula just happened to fit the data. Or we have maximal supersymmetry in string theory, and then we have 7 hyperbolic disks which scan this region. 3 alpha goes from 1 to 7, whereas R goes from 10 to the minus 3 to 10 to the minus 2. So what we may learn about SUSY M theory and string theory from the detection or non-detection of gravitational waves. The models with discrete value of 3 alpha are associated with string theory, M theory, and maximal supergravity. And there are 7 targets. And let me show you the corresponding figure. It was published in 2019, and it is kind of what Lightbird expect to see. And those are the 7 discrete targets. And they are just T models. As you see here, tanh squared for number of e-folding between 57 and 47. So if they find something here, that would be great. However, if we take continuous values of 3 alpha, then this gray band, all this area is predicted, is possible. And so it is quite possible that B mod will be discovered either above or below these hyperbolic disk targets. We simply don't know, but they still fit the data on NS as far as we have them now. And in this case, the support will be to idea of minimal n equals 1 supergravity with hyperbolic geometry. But B mods may not be detected if R is much smaller than 10 to the minus 3. If, however, the future data will fit one of the 7 discrete targets, then the cosmological models associated with string theory, M theory, and maximal supergravity will get strong support. They will certainly become favorite models of theoretical physics, which fit the cosmological observations. And we have to wait. On the other hand, Lightbird has a good hope to be launched in 2028. And let's hope that we'll find out what they will see. Thank you.
Thank you very much. Thank you very much, Renata, for this wonderful talk. So are there any questions from the audience? Please use the raise hand function to request for a question. Any questions? In the meantime, Renata, let me ask you to see your last picture you just showed.
Yes.
So it's certainly conceivable, as you mentioned, that this R value may be smaller, maybe even less than 10 to minus 3.
Let me
Yeah, just in your last figure, you showed the band, and you even commented on that the R value could be smaller than 10 to minus 3, which would be difficult to do the direct measurement from these polarizations. So my question is, are there other possible complementary studies, observational studies, experimental searches?
Sorry, I have problem opening the sharing. Oh yeah, just a second. Here.
Yeah, this is the last plot. You show the band.
Here.
Yeah, so if the situation happened to be a very small for the R value, 10 to minus 3 level, are there some observational experimental aspects that you can complement the search?
There were some discussion before COVID of the next stage of satellite missions, which will go below. But now, yeah, okay. So my husband, Andrei Linde, reminds me. So there was this conference in Barcelona where Lyman Page was on my talk, analogous. And at that time, we noticed that it is very important to improve precision on NS. And it appears that one of the planned at that time experiments, don't remember its name, also a satellite mission, might show, sorry, my slide is gone, might give us a significant improvement in precision of NS. This will be very important too.
I see.
But in principle, a rich society eventually may go to the next stage of satellite mission if they don't find anything, because it is still, still around 10 to the 16 GeV, so many, many orders of magnitude in energy to probe via B modes. So let's hope that they find something.
Yeah. Okay, thank you. So any questions from the audience? Well, if there's no more questions, let's thank Renata again. Thank you very much, Renata, for the nice talk. Okay, let's move on to the second talk of this session. It's going to be given by Professor Gary Shu from the University of Wisconsin. And the title of his talk will be Quantum Gravity and Swampland. So please go ahead, Gary, to share the slides. And you have 24 minutes total. I will remind you 5 minutes before the end. Go ahead, Gary.
Can you see my slides and my pointer?
Yes, we can.
Okay, so thank you, Tao. Let me also start by thanking the organizers for the invitation to speak. And I hope everybody is doing well. In this short talk, I would like to highlight some work that our group has done on quantum gravity and the swampland. Now, what gave string theory its appeal is not only that it offers a consistent framework for quantum field theory and gravity to meet, but also a sense of uniqueness. For example, in 10 dimensions with minimal supersymmetry, only 4 chiral theories are free of gauge and gravitational anomalies. 2 of them, with gauge group E8 times E8 and SO32 respectively, can be realized by the heterotic string. The other 2, with a large number of U1 factors, have always been considered somewhat peculiar, and I have more to say about that later. Moving on to 4 dimensions, the vacuum structure of string theory at first appears to be equally restricted. Back in the 80s, there were only a handful of known Calabi-Yau spaces, internal spaces on which string theory compactified, so few that we could even name them. Now, fast forward 30 years, string theorists have gone further in finding new ways to construct consistent chiral theories coupled to gravity. In addition to the heterotic string, we can now construct phenomenologically interesting model in basically every known formulations of the theory. In some corners of the theory, it was estimated to be as large as 10 to the 500. If you have been watching your string theory stocks lately, this number has gone up, like the price of Bitcoin, and there's no indication that. Now, I put back here in quotes because they are not necessarily local minima of a potential, as in the case of the electroweak vacuum. Even so, string theory seems to offer us an enormous number of possibilities. This is, of course, also the reason why string theory has been a constant source of ideas for physics beyond the standard model and for cosmology. But this begs the question, are there low-energy effective field theories that cannot be ultraviolet complete when coupled to gravity? And if the answer is no, we may simply bypass string theory and work directly with these EFTs, knowing that whatever we do will turn out to be okay. So this is where the idea of the swampland comes in. The landscape may be vast, but there may be an even vaster swampland somewhere out there. So the term swampland is used to refer to the space of seemingly consistent quantum field theories, which are nevertheless inconsistent when you couple these theories to gravity. So knowing where the boundaries of possibilities are, we could still try to make predictions, even though the landscape may be vast. Now the question is, what properties delineate the landscape from the swampland? And what are the phenomenological consequences? By now, there are varying degrees of understanding for different swampland criteria and how they're connected to each other. So some of the better known conjectures, such as the weak gravity conjecture, the distance conjecture, and the de Sitter conjectures are highlighted here. In this short talk, I would only be able to focus on the weak gravity conjecture, but even so, there is quite a lot to cover. Now, by definitions, this criteria or these conjectures do not follow from effective field theory considerations alone. So why are they necessary for the consistencies of quantum gravitational theories? So we are beginning to have some partial answers to these questions. In some cases, the inconsistencies of the gravitational theories may not show up to a point particle, but they may manifest when you try to probe the theory with extended objects, such as a string. And indeed, using this kind of argument, we could rule out the two anomaly-free supergravity theories in 10 dimensions with a large number of U1 factors, because there is an anomaly as seen by an extended object, in this case a string, even though from a point particle point of view, they are perfectly consistent and anomaly-free. So let me start with the weak gravity conjecture, which postulate that gravity is the weakest force. Now, of course, this is a scale-dependent statement. As you know, the strength of gravity grows as a power law in the UV, while the strength of gauge interactions only run logarithmically. So at high enough energies, the gravitational force always comes to dominate. But as you will see shortly, the weak gravity conjecture comes equipped with an ultraviolet cutoff built in, so this situation does not arise. So the weak gravity conjecture, it's really a statement about the spectrum of charge states. It requires that for every long-range force, there exists a state whose charge to mass ratio is bigger than 1, or more appropriately, the charge to mass ratio of an extremo black hole. So what that means is that if the weak gravity conjecture is right, an extremo black hole can decay by emitting this super extremo state, unless the black hole is protected by a symmetry, as in the case of a BPS black hole. Now, this is sometimes known as the mild form of the weak gravity conjecture, because we only require the existence of some state without any additional assumptions on what that state might be. Does it have to be a particle in the low energy effective field theory? And applying the same logic to magnetically charged states, and noting how the charge and the mass of a magnetic monopole scales with the electric coupling G, we infer that there is a UV cutoff that is parametrically lower than the Planck scale at weak coupling. And in string theory, this UV cutoff is a string scale, which signals the breakdown of EFT before gravity becomes strong. And precisely because of this UV cutoff, gravity remains the weakest force. Now, you can generalize the weak gravity conjecture by requiring that for every long-range P+1 form gauge field, there exists a P-brane whose charge to tension ratio is bigger than that of an extremo brane. So the weak gravity conjecture that I stated earlier is for a zero form symmetry. The zero brane that couples to the usual one form gauge field are point particles. Now you can generalize the weak gravity conjecture to higher form symmetries, but it seems more interesting going the opposite way. As Ki-Wen Choi explained in his talk, the -1 form version of the weak gravity conjecture constrains axions. However, this is also the most subtle version of the weak gravity conjecture, as I will now explain. So axions are zero form gauge fields. The -1 brane that couples to axions are instantons. They don't have an obvious notions of extremality or decay, so the usual arguments do not apply. Nonetheless, indirect arguments suggest that we can still extrapolate this bound to the -1 form case. For example, you could try to map the -1 form symmetry to the usual zero form symmetry by duality, or you can obtain this zero form symmetry by dimensional reduction. Either way, the weak gravity conjecture for axions take the form of an upper bound on the product of the axion decay constant and the instanton action. So intuitively, what the weak gravity conjecture says is that if the axion decay constant or the axion field range is super Planckian, the instanton action is small, and so higher instanton effects may become important. And more recently, we formulate the -1 form version of the weak gravity conjecture by setting this extremality bound to be given by the action to charge ratio of a macroscopic semi-worm hole. And again, intuitively, what the -1 form of the weak gravity conjecture says is that the tunneling process through a collection of small instantons dominates over the tunneling process through a single large instantons with the same charge. So there are several ways in which the weak gravity conjecture can be upgraded to stronger forms. For example, if you have multiple U1s, having a state whose charge to mass ratio is bigger than 1 in each of the charge direction is not enough to guarantee that an extremal black hole can decay. For example, a black hole with unit charge under both, like the one over here, has no decay channel. So for extremal black holes to decay, the convex hull generated by the charge to mass vectors of states in the theory should be big enough to contain the black hole region. And this convex hull condition has some implications on models of inflation with multiple axions. Now, consistencies, internal consistencies point dimensional reduction also suggest stronger versions of the weak gravity conjecture. Compactifying a theory, for instance, give rise to an additional U1, the Kaluza-Klein U1. So this gives rise to a tower, an infinite tower of Kaluza-Klein states whose charge to mass ratio depends on the radius. These Kaluza-Klein states are charged under both the U1 that was present before the reduction, as well as this Kaluza-Klein U1. And the convex hull is not guaranteed to contain the black hole region. And this suggests stronger versions of the weak gravity conjecture, which requires infinitely many sites in the charged lattice to be populated by super extremal states. So not only do we have a state that satisfies the weak gravity bound, you have an infinite number of them on the charged lattice. So what are the evidences for the weak gravity conjecture? By now, there are several independent lines of arguments that give supports to the conjecture. For example, there is an intriguing relation between the weak gravity conjecture and the cosmic censorship conjecture. But in the interest of time, let me highlight only a few ideas that have been explored, starting from attempts to prove the mild form of the weak gravity conjecture. So the mild form of the weak gravity conjecture only requires some state for an extremal black hole to decay. Can black holes decay to smaller black holes? Now, the notion of extremality is subject to corrections, whether these corrections are quantum or higher derivative. Higher derivative corrections, for example, can modify the black hole solution and the extremality bound. These effects are suppressed by the mass of the black hole. For very large black holes, this effect are unimportant. If the leading corrections increase the charge to mass ratio of an extremal black hole, like the curve A shown over here, a large black hole can decay to a smaller one. The question is, why should that be the case? And what we have shown is that for from unitarity and causality. Now, this is under the assumptions of a weakly coupled UV completion of quantum gravity. By that, what I mean is that there exists some high energy scale that I call lambda QFT. Above this scale, the usual quantum field theory description breaks down. And in string theory, this lambda QFT can be thought of as a string scale above which we have infinitely many local fields. But even that, at lambda QFT, the theory is weakly coupled. And this is the case for perturbative string theory. So we find that extremal black holes themselves can satisfy the weak gravity conjecture, at least in two classes of theories. The first class of theories are those with like scalars below lambda QFT. Again, in string theory, you can think of these like scalars as the dilaton, string theory dilaton, or other moduli stabilized below the string scale. Now, even if there are no such like scalar fields, as shown on the right, our proof still applies for UV completions where the photon and the graviton are accompanied by different towers of higher spin states, as in theories with open strings. Since we are considering the decay of a very large black hole, we can go to the deep infrared where the black hole dynamics is described by an EFT of the photon and the graviton. And to leading order, this is given by the Einstein-Maxwell action. And in 4 dimension, these are the leading irrelevant operators you can write down as corrections to the Einstein-Maxwell action. We can further use the equation of motion to recast this higher dimension operators into one of these 3 terms, the f to the 4th term, ff dual square term, and a term involving the Weyl tensor. Now, this irrelevant operators modify the black hole solution, and so the extremality bound is corrected. And the leading correction is sufficient if the higher derivative terms are small, which is the case if the black holes are very heavy. So in principle, you could calculate it order by order corrections to the extremality bound that are suppressed by the mass of the charge of the black hole. But for a very large black hole, the leading term is already good enough. So proving the mild form of the weak gravity conjecture, therefore, amounts to proving an inequality for these Wilson coefficients. And we can now show that for the two classes of theories that I mentioned, this follows from unitarity and causality. And the proof consists of two steps. First, we could show that for the two classes of theories, causality implies a hierarchy between the Wilson coefficients. And the higher dimensional operators that involve the wild tensor, parameterized by alpha 3, leads to causality violation. And we will argue that an infinite tower of higher spin states, just like string theory, is needed to restore causality. And a way to see how causality is violated by this FFW coupling is to consider a photon propagating in a gravitational shockwave background. So in addition to the usual time delay in general relativity, the FFW coupling leads to a causality violating, leads to a time helicity dependent phase shift. So one of the helicity modes experience a time advance rather than a time delay. And for sufficiently small impact parameter, the time advance dominate. Now, if your theory contains only particles with spin 2 or below, this causality violation cannot be cured. And this is because the phase shift due to a spin j particle scale as s to the j minus 1. And in fact, if you have only a finite number of these higher spin particles, this would not help either. But summing over an infinite tower of states can sometimes lead to a softer behavior, as can be seen from the rigid behavior of the string scattering amplitude. So this causality violation implies that the usual QFT description with a finite number of local fields breaks down above this scale set by the Wilson coefficient alpha 3. So if your theory contains some light scalar fields, integrating them out can generate a significant contributions to the Wilson coefficients alpha 1 and alpha 2, but not to the Wilson coefficients that violate causality. So we have this hierarchy. Now, even if you have no such like scalars, if the photon and the graviton are associated with different towers of higher spin states, we have similarly this hierarchy. And the reason is that the open string coupling is parametrically stronger than the closed string coupling. And the Wilson coefficients that parameterize the operator that violate causality receives only contributions from the higher spin states associated with the graviton. So the open string contributions to two of the Wilson coefficients will be much, much bigger, hence the hierarchy that we demand. So the next step of our proof is to show the positivity of the remaining Wilson coefficient alpha 1 by considering the forward limit of the 2 to 2 photon scattering amplitude. For the two classes of theories that I mentioned, the UV behavior is tame, and the amplitude satisfies the so-called Froissart bound and is strictly bounded by S squared in the UV. Now, the operator f to the fourth gives an S squared contributions to the scattering amplitude. Unitarity, therefore, requires this coefficient to be positive. Now, actually, to be precise, the f to the fourth coefficient can be slightly negative and still be consistent with unitarity because we are dealing with a gravitational theories. But for the two classes of theories that we consider, the dominant contributions comes from either integrating out some scalars or from the open string states, and this contribution should be strictly positive. So combining these two results, we show that black holes themselves can satisfy the weak gravity conjecture. Now, as a spin-off, we find an interesting entropy-extremality relation, which correlates the corrections to the entropy with the corrections to the extremality bound. And this relation implies that in theories that satisfies the weak gravity conjecture, meaning that this is bigger than 1, the leading corrections should always increase the entropy of an extremal black hole. And this relation is general and is not limited to the Einstein-Maxwell theory that I was considering so far. The argument is basically that for extremal black holes, the dominant contributions to the entropy corrections come from the change in the horizon area. If the leading corrections resolve the degeneracies of the inner and outer horizon of a black hole without introducing naked singularities, as the weak gravity conjecture suggests, then the horizon area should increase, hence the entropy should become bigger. However, this is not to say that the higher derivative operators are guaranteed to increase the extremality bound. There's no guarantee that this has to hold. In other words, integrating out some heavy degrees of freedom does not always increase the black hole entropy. So as an example, to illustrate that, we can consider adding a dilaton to our story. There are a lot more irrelevant operators you can write down. And what we find is that unitarity requires one of this operator to contribute negatively to the extremality bound, meaning that integrating out some heavy degrees of freedom can decrease the entropy and to decrease the extremality condition as well. Now, this negative contributions to the extremality bound seems to go against the weak gravity conjecture. However, such operator does not appear in isolation. And indeed, we have shown that in some well-motivated UV completions, for example, if the dilaton is a string dilaton with some specific couplings, the whole set of operators combine to shift the extremality bound still positively.
Gary,
and in a subsequent work,
Gary. 5 more minutes.
Perfect. Yeah, thank you. Perfect. So in the subsequent work, we examined how symmetries can impose additional structure on the effective field theory. So what we find is that these symmetries, together with either scattering positivity bounds that I talked about earlier, or the null energy condition, are then strong enough to fulfill the mild form of the weak gravity conjecture. So some of the symmetries that we consider include an SL2R symmetry or an ODD symmetry, which in string theory corresponds to S and T duality respectively. Now, since this is a SUSY conference, I should also mention the role of supersymmetry. We find that the puzzling terms, which give negative contributions to extremality, are in fact necessary to ensure that the extremality bound is uncorrected for BPS states. So the negative contributions, like coming from this operator here, are there for a purpose. So since I'm running out of time, let me refer you to the talk by my excellent graduate student, Gregory Logis, for our covariant formulations of the weak gravity conjecture. So this covariant condition, which is equivalent to what I mentioned before for the weak gravity conjecture, applies not only to charged black holes, but also rotating black holes. And in some cases, we can understand why this spinning weak gravity conjecture should hold in situations where the black hole has a holographic dual of a CFT. This inequalities follows from the C theorem of the CFT. Now, rotating black holes are unstable due to the Penrose process. So it seems like the spinning weak gravity conjecture is an overkill. But consistencies with quantum gravity, in this case holography, still demands this condition to hold. Now, showing that the weak gravity conjecture can be satisfied by a black hole is a good start, but the physics strengthen the weak gravity conjecture to a form like the one I mentioned before with infinitely many super extremal states. So it turns out for black holes with a near horizon ADS3 geometry, we can use modular invariants and anomalies to infer that there's a tower of super extremal states interpolating between black holes that we have seen before and states in the low energy effective field theory. So in this short talk, I have only highlighted the tip of an iceberg for this research program. It's reassuring to see many seemingly unrelated criteria on quantum gravity are related to each other in an intricate way. This suggests that they may be reduced to a smaller set of fundamental principles. Finding these principles would hopefully tell us a lot more about quantum gravity. So let me stop here. Thank you for your attention.
Thank you very much, Gary, for this wonderful talk to cover so much material in such a short time. So I think we have some time for some questions. Any questions from the audience? You can use the raise hand button to request for question. Questions from the audience? I don't see any questions here yet. Let me ask you a very naive question, Gary. So if the weak gravity conjecture seems to be at work, is there any preference to land in the swampland or in the regular landscape?
So if the weak gravity conjecture holds, then we would say that in theories where there's no such super extremal states, the theory is in the swampland. So the question is whether you can find such super extremal states. So what I focus on mostly is the particle version of the weak gravity conjecture. So that would be in terms of the charge to mass ratio of the state. But one can dualize the statement to axions, and it seems to be the most interesting statement one could make, constraining what kind of axion models one can construct. And of course, there are caveats. Many of these conjectures have stronger forms, and if you only can show the weak form of the conjecture, we cannot really put much constraint on low energy physics. But the goal is to strengthen as much as possible this criteria, and hopefully we will be able to be definitive about what version is correct. And if you find counterexamples, then you have to go back to the drawing board to figure out whether the model indeed has some hidden inconsistencies.
Mm-hmm. Okay, good. I see a question from Yuting. So Yuting, you have a question? Please go ahead.
Yes, hi Gary. Hi, thanks for the nice talk. I just wanted to ask for the weak gravity conjecture to hold. Strictly speaking, the charge mass ratio curve, it doesn't have to be monotonic, right? It just has to. So it's not that all and across all scale it always has to go in one direction. It can actually go up and down, as long as in the end you still have some states that satisfy.
That's right. Yeah. So we don't know. So there's absolutely no argument why it has to be A or B. It could be an oscillatory curve. And all we know is that we can usually do calculations to figure out the behavior at the very large mass limit. We only get to the first deviation from the straight line. And to get deep into the interior would require a lot of the properties. For example, we would need to use modular invariance to sort of get a spectral flow sequence of states with smaller and smaller mass and smaller charge. And to make sure that the extremality bound, we know what we're talking about, we would also need to use anomaly matching, like what was mentioned before. And that is not a result coming out for free, because we do need to assume additional things. For instance, the near horizon geometry being ADS3. So extremal black hole, by definition, in 4 dimension has ADS2 near horizon geometry, but oftentimes they can be combined with some internal, they can be combined with, say, a circle to get an ADS3. And in situations where you have a stronger knowledge about the black hole or about the spectrum of excited states, you could draw a stronger conclusion. And in such situations, we see a monotonic curve. But I do not claim to know that this is a generic behavior. It may very well be that the curve crossed the extremality, crossed the classical extremality bound and come back. Right. That would be very interesting to find out whether this monotonicity is correct or not in general.
Okay. Any further questions from the audience? Well, I don't see any further questions. So let's thank Gary again. Thank you very much, Gary, for the nice talk.
Thank
so
you.
let's move on to the last talk this session. It's going to be given by Yuting Huang from National Taiwan University. The title of the talk will be Exploring Supersymmetric Theories from Scattering Amplitudes. So Yuting, you can go ahead and share your slides, and you have a 25-minute total. I will remind you 5 minutes before the end. Please go ahead.
So is this in full screen?
Yes.
And okay, so you can see the cursor, right? Okay.
Yes, we can.
Is the cursor seen here?
Yes. Yes.
Okay, great. Thank you very much.
Yeah, go ahead.
Okay, thank you. Thank you very much for the invitation. So I'd like to take this opportunity to give an overview of some recent progress in scattering amplitudes and how it pertains to our understanding of supersymmetric theories. Now, of course, as many of you know, that n equals 4 super Yang is playing a prime role, and that it is the hydrogen atom in the field of scattering amplitude. More precisely, the analytic tools we have are mostly developed and honed in the computation of multi-loop amplitudes in maximal super Yang-Mills theory. Therefore, the state of the art of our tool set, of our toolkit, is reflected in the state of the art computations in n equals 4 super Yang-Mills. So I've just borrowed the slide from Zhang Ci in last week's amplitude conference, which basically gives a summary of our frontiers in n equals 4 super Yang-Mills, where you see at 4 and 5 point, we have the complete all loop results. At 1 loop, we have the complete all multiplicity results. And for higher other loop order and other multiplicity, we have partial results. Most of these results are given in terms of multiple polylogs, and therefore, in some sense, one bottleneck will be, for example, elliptical integrals. And actually, we have been making some progress in that direction, and that's one of the highlights in the talks of last week. Now, of course, this is the interest in computations in n equals 4 is not localized to just scattering amplitudes, but also form factors, and which also has phenomenological relevance for example, Higgs production, where in the heavy quark effective field theory, the Higgs production is given by an operator, which is Higgs GG. And this operator can be naturally included in the operators of n equals 4 super Yang-Mills, where one can now proceed and compute multi-loop corrections to this process. And indeed, tools has been developed, and we currently the state of the art is actually at 8 loop order now, which has also been discussed in last week's conference. Now, however, in this talk, I would like to take a slightly different view. I would like to go over 2 other recent developments in scattering amplitude, which was not actually geared towards the supersymmetric theories, but actually shed interesting light on various supersymmetric versions. And this is the relation between scattering amplitude and classical black hole dynamics, and as well as a recent revival of the S-matrix bootstrap. So I will go over these two topics. So first, let me talk about classical black hole dynamics. Of course, this is inspired by the recent, well, not so recent already, detection of gravitational waves, with this coming from black hole mergers. Now, in particular, we are focusing on the in-spiral stage of binary black holes. And in the in-spiral phase, the dynamics is essentially governed by the effective Hamiltonian. Now, of course, a binary black hole is a bound state. However, when we're using effective Hamiltonian to describe this bound state, one can actually analytically continue this to a scattering process, which by analytic continuing energy. So it just goes slightly be above positive energy to negative energy. And so by just doing this analytic continuation when the 2 black holes have large separations, we can glean information about this effective Hamiltonian by considering the scattering event. And therefore, we will be interested in 2-to-2 scattering in the classical limit. Now, what I mean by classical limit is that in this process, of course, we have a separation of scale. So the Compton wavelength of the black hole is much smaller than the short shell radius, and of course, it's much smaller than the impact parameter, which is the distance between the 2 black holes. Therefore, what we're really interested in is considering the 2-to-2 scattering process in the large impact parameter limit. Large impact parameter translates into small transfer captured by the Econon limit of the scattering amplitude. And indeed, by doing the multi-loop computation in the Econon limit, we've been able to compete with the standard post-Newtonian computation of the binary black hole Hamiltonian. So this is just a summary of the results over the years. Of course, the 0 PN is the Newtonian limit, and the 1 PN is when general relativity comes in. And so these are the usual post-Newtonian expansion computation over the years, which is an expansion in velocity. However, because we're extracting the information from a relativistic scattering amplitude, so for the results from the scattering amplitude is actually organized in terms of powers of coupling constants, which is G, which we call the post-Minkowskian expansion. Of course, once we get a given post-Minkowskian expansion, we can do further non-relativistic expansion to get the PN results. And as you see that the progress has been going slowly over the years, but by combining with modern amplitude techniques, we've made a very rapid progress in the past just 2 years, going from 2 p.m. to 3 p.m. to 4 p.m. now. Now, if we include spin, the story, of course, becomes interesting because we all know that the short shell black hole is the short shell solution is a unique spherical symmetric solution with asymptotic flat space-time. And therefore, when they're talking about two objects far apart, basically both short shell black hole, both black holes and neutron star, when they're far apart, to a leading approximation, they look the same. They're just point-like objects. However, when the object is actually spinning, now that even though they're very far away, they can actually start to look very different. And to see this, you can actually just think of how we describe a point particle that spins in the world line description. So if we talk about in terms of a world line, then what one will need to do is introduce a new degree of freedom. Let's call it the spin operator, which describes the spin part. And just even at leading order, we have an infinite number of operators that we can attach to this world line. This is the leading order in terms of leading order in the Riemann tensor. And so this is essentially, these are essentially the multiple moments of this spinning objects. So since we have infinite number of operators, even at the leading order in Riemann or coupling to the gravitational field, therefore that means that we have infinite number of Wilson coefficients. So different spinning objects actually look different, depending which is encoded in the Wilson coefficients. So of course we can just directly take the Kerr solution and then compute these Wilson coefficients. So in this particular normalization, the Kerr solution corresponds to when these Wilson coefficients are set to 1. For neutron stars, then these coefficients will be slightly different. So when we add spins even far apart, we have a distinction between neutron stars and black holes. So in this language, one might ask, what is special about these Wilson coefficients when the Wilson coefficient is set to 1? Okay, in other words, is there some new principles that are behind this that tells us that that something special will happen when the coefficients is set to 1? Now, to answer this, since this is about this amplitude is describing the transition between two incoming states with a particular spin orientation to two outgoing states with particular spin orientation, we can imagine that this econol amplitude as a matrix, literally an S matrix element, acting on the spin Hilbert space. So we can first truncate the Hilbert space with finite spins and then consider this econol S matrix. And for example, an observable you can compute is, let's say you have two spins coming in, and let's say it has a particular spin entanglement entropy. And then we ask, after this scattering process, it goes out, what is the change in the entanglement entropy? So what is the difference between the spin entanglement entropy of the incoming state and the outgoing state? So we have some incoming state with particular spin orientation. We act with this econol S matrix to get the outgoing state. And we just compute the difference between for example, the von Neumann entropy between the in and out. And of course, our econol, since our econol S matrix is basically, it's basically parameterized by these Wilson coefficients. Now we can tune the Wilson coefficients and see how the spin and the relative and spin entanglement entropy changes. And so this is a recent plot of the computation. So this is a plot of the change at delta S is a change in this spin entanglement entropy. And you'll see that there's a dramatic decrease in the change in entanglement entropy when the C values, when these Wilson coefficients are tuned to black holes. So said in another way, it seems very remarkable that we have two objects coming in exchanging multiple gravitons, and somehow when these objects are tuned to black hole spinning values, then all of a sudden it's as if nothing happened. Whatever the entanglement entropy state, it can be a pure state or a mixed state, whatever state it came in with, essentially is going to come out with the same configuration. Now, I like to point out that this, so we call this the suppression in relative spin entanglement entropy, change in spin entanglement entropy. This phenomenon was actually also observed 2 years ago in the process in nuclear physics, where people look at the low energy baryon interaction, and also they look at the spin entanglement, the changes spin entanglement entropy, and they found that there again is a shutoff where there's a spin suppression that happens in the baryon interaction when one is actually sitting on a symmetry, when there is actually emergent symmetry. So for example, there's a famous emergent SU4 symmetry, and they've computed the scattering phase and showed that there's actually entanglement suppression exactly at this emergent symmetry. So it seems to apply that there's some emergent symmetry at play, because we're also observing that when we tune to black holes, there's also the spin entanglement suppression. Here they were computing the entanglement power, which is related, which is related to what we've been computing, but which is basically measuring how much the change in spin entanglement occurs. Okay, so so we've seen that looking through the Econo S matrix can allow us to learn a lot about the dynamics of black hole. So what does this tell us about supersymmetric black holes? So for example, a couple of years back, Simon Karen-Hoyt and his collaborator, they looked at using the scattering amplitude, the Econo approximation, to look at the orbit of black holes in maximal supergravity. So for example, let's just consider the 1 p.m. effective Hamiltonian, which you can parameterize by in these parameters. Then we just directly extract information of these parameters. As I mentioned before, you can directly extract information about this by matching it to the scattering amplitude. So these are essentially, you can think of them as n equals 8 scattering amplitudes. And at this order, you will need first the tree level as well as the one loop scattering amplitude. Now from this, you can, by mapping to the onshore scattering amplitude, you can start to fix these 1 p.m. Hamiltonian. Once you have the 1 p.m. Hamiltonian for two black holes and n equals 8 supergravity, then you can compute various quantities. So for example, there they computed the change in the Laplace-Runge length vector, which is basically controlling the precision of the orbit. And they find that if you directly match to the amplitude, this factor, let me call it F naught here, is actually 0. So that means that there is no precision for maximal supergravity black hole. And this 0 here can actually be understood from the scattering amplitude from a very famous property, and that is that in n equals 8 supergravity, when you consider multi-loop amplitudes and you put it in a suitable basis, there's actually always no triangle subdiagrams. So the so-called no triangle theorem or no triangle diagram property of n equals 8 scattering amplitude directly translate to the vanishing of this precision factor. And therefore, since we know that the no triangle theorem is valid to all loop order in perturbation theory, therefore the black hole orbit does not persist to all loop order, and therefore the orbit is integrable. Okay, so in other words, even though this is a gravitational theory, actually there is in a very precise sense observables in this theory which are integrable. Now, previously I mentioned about the spin entanglement entropy change. So one can also look at spin entanglement entropy change for rotating black holes. So this is the work that I've done with a few of my students last year. So for example, we consider n equals 4 non-BPS rotating black hole, and whose solution was written down in 92 by Ashok Sen. And first of all, we construct the econo amplitude for these n equals 4 non-BPS scattering. And we verify the econo amplitude indeed describe the classical dynamics of the black hole by matching the impulse that you get from the econo amplitude with what you will get from computing the geodesic with respect to this rotating black hole background. And we verified that it actually exactly matches. Once we have the econo amplitude, then we can again compute the change in spin entanglement entropy. And in particular, we can have analytic control in the econo phase, in the spin space. And so if you look at the econo phase and the spin space, you'll notice that, so the diagonal part is the component where the spin orientation does not change. And therefore the off diagonal part corresponds to process which its spin orientation is changing. And so you see that the z square minus 4 factor is appearing all over the place in the off diagonal part, which means that in the BPS limit, the spin deflection is minimized in the BPS limit. So again, what that translates to is that the spin entanglement entropy gets maximally suppressed in the BPS limit. Okay, so once again, we see that we observe spin entanglement suppression when the configuration of this black hole seems to have some enhanced symmetry. So it'll be nice to understand what exactly is this enhanced symmetry and how precisely this enhanced symmetry plays from first. I mean, this is just direct computation, so we would like to just derive directly the relationship between the enhanced symmetry and this spin entanglement suppression. Good. Let me now switch to the other developments, which is the revival of the S-matrix bootstrap program. And first of all, of course, the whole idea between the S-matrix bootstrap is that we want to carve out the space of consistent theory by carving out the space of consistent scattering amplitude. And now, what do we mean by consistent scattering amplitude? Well, we mean by we follow two basic assumptions, which the first is that in the physical regime and high energy, that scattering amplitude is bounded. So basically, from various arguments from unitarity to causality, you can argue that the scattering amplitude is bounded by S squared, or said in another way, that there exists a twice subtracted dispersion relation for generic scattering amplitudes. The second assumption is that when the t is below the threshold, the scattering amplitude will be analytic away from the real axis. So there's no, for example, anomalous singularities on the complex S plane. So with these, you can then, depending on your flavor, we can start to impose unitarity, locality, and crossing symmetry in different ordering and extract information and constrain the S matrix element. So as you can see, just in the past 2 to 3 years, there's been various different developments built on different starting ansatz and then starting assumptions and then imposing further and further constraints. So for example, one can start with local and crossing ansatz and then impose non-perturbative unitarity. The more conventional approach would be to start with the dispersion relation at fixed impact parameter, fixed t, or which already manifests locality and unitarity, and then we impose crossing symmetry. And of course, one can just directly find another representation, which is just implement crossing and unitarity in the very beginning in the dispersion relation, and just see directly what this implies. Now I'm going to focus on the fixed t dispersion relation, and the reason is because for the fixed t dispersion relation, we actually have a mathematical precise definition of what the space is carved out by this. What is the space that is carved out by this? By this constraint. And basically, the statement is a one-line statement. The space is characterized by a positive geometry, where this positive geometry is just the convex hull of what we call the product moment curve. So just to give you a more precise definition, so the statement is that you can start with a product with for example, these A elements that corresponds to the convex Hall. The convex Hall meaning that it's written as a positive sum of product moments. So these are moments because this is related to the spin of the state. So these are, you can see that this is 1j, j squared, j cubed. This is a moment. This is related to the mass of the UV spectrum, where it comes in as 1 over m squared, 1 over m4, 1 over m6. So these are also moments. So the statement. Okay, great. So this, okay, sure, no problem. So we have that you have this, you start out with the A space, which is governed by the convex Hall of this moment. Then the physical coupling of the space is just very simple. So once we have this space, whose boundaries are precise, are already well studied in mathematical literature, then we just need to do a rotation to get the S-channel contribution to your EFD coefficients. And then you do a further projection to incorporate the U-channel contribution. And then you can impose symmetry to carve out the space and the effective coupling. So just to give you a simple example. So for example, for the 6th derivative and 8th derivative operator, so let's say we're interested in concerning these Wilson coefficients, some of them are already related by crossing symmetry. So once again, we just write out the boundaries that are associated with this product moment geometry. So these are the boundaries. We do a rotation to the S-channel space. So this is the region that is carved out by the S-channel space. And then we further do a projection, and this is the final result. So here we give the finite result of the space that is given by G40. This tilde means that it's normalized by G20. So this and G31 normalized by G20. Once again, 402, these are just labeling the Wilson coefficients. So interesting, so you can see that the space that is carved out is extremely finite. It's a very tiny region. So it has an upper bound of 1. And this is not just numerical carving, these are analytic carving out. So we have analytic expression of these boundaries. And you can actually verify these this space by doing numerical analysis, which is by doing, for example, semi-definite programming, and you can find exact match with this analytic space and the numerical approach result. Now, of course, many of you who thought about dispersion relation know that there's actually an issue associated with massless particle. And for example, if you want to govern this, if you want to talk about the space of scattering amplitude for massless particles, then generically, once we include gravity, there might be a problem because for gravitational theories, there exists a gravitational pole, which means that since we're looking at finite t, at the near forward limit, which we're fixing t to be close to 0, this graviton pole will diverge, and this will affect our ability to impose dispersion relation. So from a recent result of this year by Simon Kieran-Holt and his collaborators, they've developed a finite impact parameter approach to applying to the dispersion relation. And just to show you their results, so for example, if you don't have gravity, so this is the bound on exactly the same plot I gave before with using this finite impact parameter approach. And this is for d equals 6, but so this bound looks slightly different than the one that I've just displayed here, but you can see that it's similar. And in fact, if you put d equals 4, they're exactly the same. So as you can see, the forward limit bounds that are carved out by this analytic geometry I discussed before exactly matches with this finite impact parameter bound. So these are exactly the same results. Now, but if you have gravity, then the relation, then the bound starts to change. But because of the fact that they're an impact parameter, finite impact parameter space, they can give precise bounds for even when gravitational effects are included. So these are, for example, the G square, which is the 4th derivative S square operator and S cube operator, the relative coefficients, and these regions are carved out by the finite impact parameter dispersion relation. Now, of course, the point is that what this implies for SUSY. So, for example, now once again, so since these are really general approaches, so one can apply this approach to supersymmetric theory. So, for example, let's assume maximal SUSY. So, when we assume maximal supersymmetry, then the 4-point amplitude naturally has a prefactor which is dictated by maximal supersymmetry and gravity, and this prefactor corresponds, for those who are familiar with this, corresponds to an overall R to the 4 operator, which you can just subtract out sitting in front. What this means is that after the subtraction of the R to the 4 operator, then this amplitude no longer needs subtraction, and we can actually bound the coefficient of G0, which means that we're bounding the coefficient for R to the 4. So once again, applying, so Simone and collaborators, they apply their finite impact parameter bootstrap to bound the coefficient for G0 for maximal SUSY. And in 10 dimension, they give this range between 0 and 3. And this is normalized by some UV cutoff, which is below the string scale. Below the M Planck. And of course, you can compare this to known maximal supersymmetric theories. And for example, if you compare to type 2b value, the type 2b value is 2.4, which is slightly smaller than 3. But this is important because this 3 here is when you basically throw the kitchen sink to the problem, which is we're assuming we're extracting all the information from unitarity, crossing symmetry, and so forth into the problem. And we still see that there's actually a mismatch, a sliver of region between the string theory values and actually what is actually allowed from unitarity. So we can ask this question: can we even? So as we often say, string theory is the only game in town. One can pose an even sharper questions of this type, which is: can we actually show in 10 dimension maximal SUSY that this 2.4 value, that is there a way to close this this mismatch between the string theory value and the value that is dictated by unitarity and all the underlying principle? Or put in another way, is there actually some model here that is also maximal supersymmetric in 10D that actually saturates this bound? Now, there's also, as I mentioned in the beginning, there's also non-perturbative analysis ways that you can bound. And for the non-perturbative analysis here, you no longer need a new scale below the M Planck. And so there in the non-perturbative analysis, they can bound this R to the 4 coefficients from below, and they have a lower bound of 0.13. And you can compare to either 2A or 2B. So for 2B, because of S duality, you have the complete non-perturbative result for this coefficient, and you can see that the non-perturbative result has the lowest value of this non-perturbative result, which depends on what you take for tau bar, is 0.13, and you see that this is very close to the lower bound of 0.13 here. Generically, 2A is bigger than 2B. Okay, so I think I will end here, but I hope that in this talk I persuaded to you that really there's a very fruitful interplay between supersymmetric theories in the field of scattering amplitude, not only in that we use it as a tool to as a playground to develop our analytic tools, but also in the other way around, when we're asking questions, interesting question in scattering amplitude, we can turn around and shed new light on known theories, as known supersymmetric theories, that then reveal new properties that was not appreciated or not even known before. So thank you very much for your time.
Thank you, Yiting. It's a very nice talk. So let's see, we may be able to entertain a few short questions. Any questions from the audience? Yes, Gary, please.
Hi, so beautiful talk.
Thank you.
I'm intrigued by this suppression of entanglement entropy that you were talking about in your talk. If this is a symmetry reason why the entanglement entropy is suppressed, why shouldn't it be 0 instead of suppressed? And in the so maybe the second question is, in this other paper that you reference in nuclear physics, what would be the equivalence of the Icono approximation, Icono limit that shows the symmetries?
So in both cases, I think my memory is a little bit vague on this, but I remember. I mean, so of course in the Icono limit, one of the as you know, one of the good properties that you can do for Icono limit is that you can resum the all loop results. So it's all loop resum, so you can do the full complete non-perturbative analysis. Now, for the first question about the suppression of why is it not exactly zero? So there, the statement is that it's actually is zero, but there's actually limits where it's actually exactly zero. And so here there's no numerical value here, but this is actually very so. The reason is that when we're considering this, you're considering a scattering event with, and you can parameterize it by the center of mass momentum with respect to the mass of the object. So in the ultra-relativistic limit, and when we have the C set to 1, it's actually literally 0. So indeed, in the ultra, but when you're going away from the ultra-relativistic limit, or more precisely, when you go to the non-relativistic limit, then you start, because of non-relativistic, you're really at low energy, so it starts to deviate a little bit from 0. But in either case, it's always the global minimum. And when you go to the ultra-relativistic limit or the high energy limit, it's directly 0, indeed.
Okay, so in the nuclear example, it's also not exactly 0 because they are non-relativistic.
Yeah, because these are low energy analysis. Yeah.
Very nice. Thank you.
Sure.
Thank you very much. In the interest of time, I think we can stop here for this session. So let me thank all the speakers again, and let's take a short break for this session, and we'll come back at 9:45 for the final session. Thank you all.
Okay, thank you.
And see you soon.
Hello, everyone.
Hello.
Maybe we'll start the last session. The first talk of the last session is from Professor George Leonates from University Ioannina, Greek. He will announce something important. Welcome, please.
Thanks very much for the invitation. Can you see my screen?
Yes, sure. Can you please full screen?
Yes, of course. Okay.
Yeah.
Thank you very much for the invitation. I will announce the conference of SUSY that will happen next year in my hometown in Ioannina. China has put very high standards, so we have to make a big effort to do something good. So let me start my presentation. It is a great honor of us and a privilege for us to host the International Conference of Supersymmetry and Unification for the year 2022. The conference will be organized by the Physics Department of the University of Ioannina from Monday 27th of June to Friday 1st of July. As it is customary, the previous 3 days will be devoted to the pre-SUSY summer school, usually attended by graduate students and postdoctoral fellows. Now, in addition to the information regarding the organization of the conference, I will seize the opportunity to say a few words about the University of Ioannina, the Physics Department, and the city of Ioannina. So the University of Ioannina was founded in 1964, initially as a charter of the Aristotle University of Thessaloniki. Thessaloniki is the second biggest town in Greece after Athens, which is the capital. The university became independent and was named the University of Ioannina in 1970. Here is a partial view, as you can see, of the buildings of the university and the surrounding area. The University of Ioannina is amongst the well-established universities in Greece, consisting of 11 schools with 24 departments and more than 25,000 students. The campus is located about 6 kilometers of the city center. It is one of the largest university campuses in Greece, with area about 3,500 acres and 236,000 square meters of buildings. We are about 550 teaching and research staff and 300 administrative personnel and technicians. The university can be reached by car and public transport in 15 minutes from the city center. Now about the physics department. It was also founded the same year, 1970. The faculty consists of 45 members, 100 postgraduate students, and more than 30 PhD students at the moment who conduct top-level theoretical and experimental research. The teaching and research faculty members provide high-quality theoretical education and practical training in physics and other related fields to more than 1,600 students of the department. In this picture, you see the buildings of the department. And now about the organizing committee of the conference. The organizing committee consists of faculty members of the theoretical physics and experimental high energy physics division of the University of Ioannina of the physics department. The following members participate: Athanasios Dedes, who is doing beyond the standard model physics and supersymmetry; Ioannis Florakis in string theory; Panagiotis Kandi in gravitation and cosmology, Panagiotis Kokas, who is the head of the department and in CMS experiment, myself, Ioannis Papadopoulos, who is also in CMS experiment, Leandros Perivolaropoulos, who is in astrophysics and cosmology, John Rizos in string phenomenology, and Kyriakos Stamvakis, well-known expert in supersymmetry, and he is also doing cosmology these days. The physics department has a strong focus on theoretical and experimental high-energy physics. The members of the theory group conduct research on particle physics, theories beyond the standard model, supersymmetry, superstring theory and phenomenology, gravity, cosmology, and astrophysics. The members of the experimental high-energy physics group collaborate with groups at CERN and participate in particular in CMS and ATLAS experiments at LHC. In the physics department, there are also other research areas, including solid state and condensed matter in theory and experiment, laser and nuclear physics, atomic and molecular, and so on. So about the experience in organizing conferences, I will remind you that during the last 3 decades, the theory physics section has successfully hosted many national and international conferences, including the Planck 2015 conference. Some of you were there. It was late of May with 220 participants approximately. It was also next year the string phenomenology 2016 with something like 130 participants. And here you can see the posters of these 2 events with the pictures of the theater of Dodoni and the lake of the city. So now about the hotels and the conference center in particular. The conference center will be in a prestigious location of the center of the city, where it's the hotel, 5-star hotel Grand Serai, which is surrounded by 13,000 square meters of garden and green places. The hotel combines the traditional style and color of the Epirus area with the utmost modern luxury. The standards of the hotel facilities have high specifications for exhibitions and special events and banquets. The hotel may offer accommodation to all the participants of the 2022 conference with the following specially negotiated rates for us, which can be extended for the weekends before and after the conference. So, for example, for a single room and breakfast, it costs 80 euros. For a double room with breakfast, 90 euros only. Here is a partial view of the hotel with a swimming pool. And here is the main entrance of the hotel, the interior, and you see the gardens outside. So the Grand Serai Hotel facilities include fully equipped conference rooms and, of course, wireless internet access everywhere. The main conference hall can accommodate more than 500 participants, and there are also 5 rooms with capacity of 100 people or so for parallel sessions. Of course, in the surrounding area, there are numerous hotels in the city with reasonable prices, even they start from 30 euros and more for the participants who don't like to stay there and wish to stay in an alternative accommodation. Yeah. Here is one of the rooms of the hotel, as you can see. So, concerning the program, we follow the usual timetable, and the conference will run from Monday morning to Friday afternoon. The activities of the SUSY 2022 will be scheduled according to the following tentative program. In the mornings, we have plenary talks always, and early in the afternoon, of course. We have also parallel talks later on, and the first day after the talks, we have the reception. On Tuesday, after the talks, we have an open talk, which is for the public, and it will be given by some expert in supersymmetry. Wednesday afternoon, we will have an excursion in the surroundings. I will show you some pictures. And Thursday, after the talks, we have the banquet in a nice place with very good local food. And finally, Friday will conclude with the parallel talks, and then for the weekend, we can organize small groups for those who stay there. So the city of Ioanna, let me say a few things. Ioanna is the largest city of the region of Epirus. This is the name of the region. The municipality has about 120,000 inhabitants. It is built near the lake of Pamvotis. It is 480 meters above the sea. The foundation of the city has been ascribed to the Byzantine emperor Justinian in the 6th century AD. However, recent research has uncovered evidence for Hellenistic settlements. Here you see the city, partial view, and the lake. There are many places to visit in the city. I just mentioned a couple of them. You can see here the old town of the city, which is inside the castle of Justinian, and the houses in the traditional style of the old period. And just opposite this, you see an island, which is in the lake, inhabited. And you can see also here in these pictures, nice streets of the old city, and also cafes and restaurants in the lakefront where you can enjoy your dinner and coffee. The surroundings now, there are many historical monuments in the area, including the archaeological famous site of Dodoni, where the theater you can see here is one of the most important and perhaps the oldest in Greece. In full capacity, this is something like 70,000 people who could attend the events in the old days. We can visit this, it's a very nice place. Also in the surrounding areas, which are easily accessible in less than an hour from the city, there are abundant with beautiful landscapes and forests, rivers, gorges, and many other things like villages and seaside locations. Here there are some masonry structures, the bridges, famous bridges, and these are 2 of the 5 rivers of the area. Here you can see a very deep gorge, one of the deepest in the world, which is called Vikos. Here you see rocks on the top of a mountain and some old style houses and picturesque villages in the old style of the 17th and 18th century. And also you can see here some type of monasteries which are built in the caves of rocks, as you can see. Now regarding the ways to reach Ioannina, Ioanna, first of all, is connected to the capital of Greece, Athens, and the international airport. There are 3 flights every day from Athens to Ioannina. The duration of the flight is about 50 minutes. But beside this, there are also other international airports that one can reach easily Ioanna through highways. I just mentioned here the Thessaloniki International Airport, which is located something like 260 kilometers, and you can reach it in 3 hours by car, driving through very nice landscapes. So the rest of them, you will see it in the transparencies later. I don't want to waste time for you. to you, your time. So also Ioanna is connected with highways to Athens in it's about 400 kilometers far away. You can see here the maps of the highways and how you can reach Ioanna. Here is Athens, and here is the city of Ioannina. Here is Greece. And there is a second map which shows how you can come from Thessaloniki to Ioannina, and estimates by Google as we see the time. And here you can see the international airports, which are closer to Ioannina and Thessaloniki, and also Athens, which is connected, as I told you, by everyday flights. So this is what I wanted to show you: Athens-Ioannina highway and Thessaloniki-Ioannina highway. There are also other ways to reach Ioannina. You can see them in other places in the internet. So we are looking forward to welcoming you in SUSY 2022 in Ioannina. Thank you very much for your attention.
Thank you very much, Professor Leontarius. You gave a very comprehensive, very interesting, attractive introduction and announcement. I think everybody are looking forward to join the next meeting next year. The only problem is whether we can by then participate in the meeting personally, not like this year online.
Yeah, let's hope that we can do something next year, but everything, as you know, depends on the pandemic, on the evolution of the pandemic.
Yes.
We will discuss the details in the future time with the International Organizing Committee and decide about this. You will be informed soon about this.
Okay. Yeah, we still have a couple of minutes. Anyone have any question about the next meeting? Seems not. Okay, if not, thanks, Professor Leontarius again. Okay, then we come to the very last summary talk from Professor Hitoshi Murayama, University of Berkeley. Of course, normally, as usual, last but not least, maybe most. Let's look forward to his talk. Yeah, Professor Leontarius, can you stop the sharing?
Yeah, of course I will do it. I'm just lost in this.
It's a beautiful picture, though. Too bad to lose it.
Yes, so somewhere it says stop. No, it's not here. Where is this thing? Okay.
Maybe I can force it.
Can you force it? Okay.
Great. Yeah, please go ahead.
What?
Yeah, please full screen. Yeah.
Okay.
Yeah, great. Please.
Okay. So let me get started. And I have to make this smaller to get it out of the way. All right. So first of all, thank you so much for the invitation to give this concluding talk at this very interesting conference, SUSY 2021. And this is actually the second time I had an honor of giving a concluding talk at the SUSY conference. The last time was actually Melbourne, and that was in 2016. And so as you can see, we had actually in-person meeting back then, together with a lot of wine. And unfortunately, we can't meet in person this time, but nonetheless, the physics, of course, goes on. There has been a lot of interesting talks here. So one thing we, of course, all know is that the standard model is a fantastic accomplishment of a community as a whole. The particle physics started by the discovery of the electron by J.J. Thomson towards the end of the 19th century. And it took more than 100 years to come up with a theory of the microscopic world that is capable of describing all the particles and interactions we know. So this is a fantastic success. And indeed, the current LHC data shows beautiful agreement between what we can predict based on the standard model versus experimental data. But nonetheless, we were all hoping to discover also something beyond the standard model and physics. And of course, there have been so many different searches going on. And this particular slide is from Atlas. You see that all these the searches end up with a very strong limits right now, and no clear discoveries of new particles beyond the standard model. So to some extent, this is a little disappointing. And so with the discovery of the Higgs boson in 2012, so this actually filled in this bullseye of this chart of particles, and the standard model does become complete, but we are still not happy about this. And that's why we are talking about supersymmetry or in some other forms of the physics beyond the standard model. Specifically about supersymmetry, we talked about many different reasons why supersymmetry is interesting. It is interesting mathematically. String theory needs it. It gives us rationale why there are scalar particles beyond fermions and gauge bosons. It may help stabilize inflaton potential, even though getting the flat inner potential is still a difficulty, but nonetheless, it makes the potential more stable against radiative corrections. It can achieve the gauge coupling unification. It does give us the dark matter candidate. It may solve the hierarchy problem or naturalness problem. And if supersymmetry exists, of course, it would be great fun for collider experiments, because all of a sudden we're doubling the number of particles and we have many different signatures we would like to sort out. And so that will be, of course, a lot of fun. It may also help us achieve baryogenesis. It may also help us a little bit in understanding cosmological constant. We heard about, for example, the zero swamp Planck conjecture earlier today. And so the cosmological constant is fine-tuned compared to Planck scale by 120 orders of magnitude. If you bring in supersymmetry, you solve the half of the problem. So 120 orders of magnitude becomes 60 orders of magnitude. There's still 60 orders of magnitude to go, but anyway, it's an improvement. And so there are plenty of reasons why supersymmetry is still interesting, despite the lack of signature at the OHC so far. And unification is another main theme of this conference. And we all know that Newton unified planets and apples, and there came out the laws of gravity and mechanics. Maxwell unified electricity and magnetism into electromagnetism. Around the time of the Einstein, there were scattered phenomena in quantum mechanics, in atomic physics, in nuclear physics, alpha decay, beta decay, and gamma decay. And of course, we all know that Einstein somehow didn't decide to believe in quantum mechanics at all. And what he did is to reconcile the electromagnetism, which has Lorentz invariance, with the Newtonian mechanics into special relativity, and then unified it together with the gravity, which was, of course, a singular achievement by Einstein. At the same time, there was enormous unification that happened since then, namely that the QED includes special relativity, electromagnetism, quantum mechanics, and nuclear physics like gamma decays in essential fashion. And we all know that this unification has an incredible power of predictivity, predicting the electron, for example, G-2 at the level of 12 significant digits for the electron. And there's an interesting puzzle going on with the muon, as we all know. So we'll see what will happen from what we can learn from there. And in addition, from other phenomena in nuclear physics, we learned the existence of the strong force that also binds the nuclei together, and the weak force that lets the particle species change, including beta decay. And we have basically just achieved this new layer of unification of the electroweak theory with the discovery of the Higgs boson. So we have come a long way indeed. Beyond this, we don't know, but there is the possibility of grand unification that was also talked about this conference, and hopefully so a true unification, which includes both quantum physics and the general relativity in an essential fashion, such as string theory. So unification, of course, has been our dream in understanding the physical world and our universe. And of course, you have seen this a picture many times by now, but the unification seems to happen a lot better with supersymmetry than without supersymmetry. And this is also very interesting from the experimental point of view now that the hypercamiocande due and being built, and the hypercamiocande would extend the reach on proton decay to positron pi naught by another order of magnitude up to 10 to 35 years, which is really amazing. And DUE would do the same for the more sort of supersymmetric favored mode of proton decay to K plus in nu bar. So there's an area we definitely look forward to in experiments in the near future. At the same time, we did hope, at least I did, to observe some interesting signature for supersymmetry at the OHC, and we all know that that hasn't happened, at least yet. And the LHC could have told us many interesting things about the origin of the symmetry breaking, from rigidity breaking from supersymmetry, origin of naturalness, dark matter, baryogenesis, something unexpected. And so far, of course, the supersymmetry was supposed to be candidate for all of them, but no clear experimental signatures for them. So that's where we got stuck a little bit on what to do. And so, because I was hoping for discovery supersymmetry sometime in the near future, I even had a talk like back in the beginning of the century, presenting this kind of a mock-up of the particle listing in particle data group, talking about, for example, squark mass, and measuring the spin is difficult. So J equals 0+. It says that there's a ambiguity interpretation between minimum supergravity versus the universal extra dimensions, and then there can be different decay modes. Some of them have to assume certain things to interpret the data. But anyway, so this was just fun to make. We had to see that. I still do think, though, that one motivation for supersymmetry, namely naturalness, is a good motivation. And I still take this point of view very seriously. So the idea of naturalness, that if you think of, for example, the mass of the electron, knowing classical electromagnetism, there was actually a naturalness problem towards the end of the 19th century. And it hadn't been talked about this way, but there was, because the electron creates a Coulomb potential around it. It feels its own Coulomb potential, which is linearly divergent. And if you think the size of the electron is as small as what we know today, namely less than 10 to the minus 17 centimeters, that alone gives you a whopping GeV contribution to the mass of the electron, even though we know the mass of the electron is a half MeV instead. So that is already calling for a fine tuning at the level of 4 orders of magnitude in cancellation. And so that's the naturalness problem. But it turns out that this problem had been solved by the discovery of the quantum mechanics and antimatter, because the quantum mechanics allows for uncertainty principle, so that what we think is the vacuum is constantly creating E plus E minus pairs within the time given by h bar over delta E, E given by 2mc squared over here. And because of the antimatter, we have positron, so you can create them in pairs as a result. So knowing quantum mechanics and antimatter, then this process is immediately, we know is happening all the time in what we think is the vacuum. And when we place an electron in this vacuum, sometimes the electron you placed notices that there is a positron around it because of this quantum fluctuation and decides to annihilate it. Then the electron that used to be part of the quantum fluctuation now remains as a real particle. So this is yet another process that can happen in addition to this Coulomb force. And it turns out that the Coulomb force and this new process exactly cancels with each other, leaving only logarithmic correction, so that the correction is only logarithmically sensitive to the size of the electron. So even if you believe that it is as small as the Planck size, then this correction is only like 10% at the end of the day. And then there's no fine tuning at all. So the idea of supersymmetry is that the history repeats itself. So we double the number of particles by introducing the antimatter. And we do that again by introducing superpartners. Then there's again precise cancellation between these diagrams, leaving only logarithmic sensitivity to the size of the Higgs boson in this case. And so that the standard model can be applied to much higher energies, so that we can talk about things like unification at high energy scales and string theory and so on and so forth. So I still do take this kind of a point of view seriously, even though LHC hasn't seen the signal yet. So hopefully it is actually there, relevant for this problem at the slightly higher energy scale we hope to reach in the future. And one reason why I still take this point of view is that the naturalness is known to work. The reason why inflation theory had been proposed initially was based on the idea of naturalness, namely that how do we understand there seems to be correlation of CMB photons coming from different parts of the universe that seems to go beyond the causality, and that's the horizon problem. Our universe also seems to be very flat. The Planck data says it's as flat as 1% level, and the curvature is supposed to grow as a function of time. So that was a fine-tuning problem to make the curvature very small as the initial condition of the universe. And there's a lot more entropy than the matter there is. and the universe itself is very big as a result. And then the fluctuation seems to be very Gaussian. And so all of these things pointed to inflation as a naturalist argument. But now we know that this actually works extremely well in terms of providing C's for the density fluctuation due to the quantum fluctuations during the de Sitter phase of inflation. And the data seems to agree extremely well with that hypothesis. So naturalist argument at least worked here. So we hope that it would work in the electric weak scale as well. But nonetheless, of course, the media made fun of us, saying that this is a crisis in physics. If SUSY doesn't pan out, scientists need a new way to explain the universe. So we'll see. And indeed, many of us started to think about other ideas beyond supersymmetry, which may help us understand the various issues like dark matter baryogenesis and so on and so forth. So in some sense, the community became even more active by the lack of signal of supersymmetry at this moment to come up with new ideas, new possibilities of experiments and so on and so forth. So it's actually a very lively period of time. And of course, this kind of, being made fun by the media about a field, we have been there before. This is an article I remember back in '93 talking about 315 physicists reporting failure in search for supersymmetry by the CDF experiment at Tevatron. So we've been there before. So let's see. So you can also think about there are reasons why supersymmetry shouldn't be there. And people often talk about the flavor problem. Once you have the TV scale supersymmetry, that can lead to too large flavor change neutral currents. It can lead to too large CP violations, such as the EDM of the electron. Now there's a very strong limit from Acme collaboration. Gravitino can often cause a problem in early cosmology and destroying the Big Bang nucleosynthesis theory, for example. And proton decay so far hasn't happened. As some SUSY gut predicts the proton decay rate faster than the current limit. And SUSY breaking models tend to be contrived. There is also a naturalness problem in SUSY guts, such as the triplet doublet splitting problem. And the mass of the Higgs which we discover seems to be a little too heavy for the minimal supersymmetric standard model. And of course, there is no experimental signature so far. So there are reasons why supersymmetry may not be there. So we have to keep arguing about it until we have some definitive results from experiments, hopefully in the near future. One thing which I care a lot about the supersymmetry is that it does provide rationale for the existence of scalar particles such as the Higgs boson. So far, Higgs boson is the only spin zero particle in a standard model. This is the only spin zero elementary particle we have ever seen. And this is kind of strange. When I was first learning about this back in grad school, I couldn't believe this because being spin zero means it doesn't have a face. It's totally bland and isotropic. And all the other particles have spins, or spin 1/2 or spin 1, so it has an orientation. They have phase, but Higgs boson doesn't because it's a spin 0. So this is actually kind of spooky to begin with. And this is the only particle of that kind. It doesn't seem to have any context at all. And so it's actually a standalone particle with no context. And we actually are making it to do the most important job in the theory, even though this was the kind of particle we had never seen before. And so this sounded very artificial to me, like a wishy-washy thinking. So I couldn't believe such a theory back in grad school. So, and we still don't know what dynamics there is to make the Higgs boson condense. Again, supersymmetry does provide the reason for this because the Higgs mass squared is driven negative from the renormalization group evolution due to the large Tokugawa coupling. So in that case, we know why Higgs boson condense. And that's there are plenty of other scalar particles in supersymmetric theory, but the other ones are unlikely to acquire expectation values because of their gauge quantum numbers. And Higgs is the most likely one to condense because of this large Tokugawa coupling effect. So we can explain why this particular particle is condensed in the universe today. So it does definitely provide rationale for the existence of a particle like Higgs, existence of scalar particles in general, and even providing dynamical explanation why it is this particle that condenses in the universe do the most important job in a standard model. So this is actually an important point. And so, of course, we didn't know this till 2012. So because I didn't like the idea of the Higgs boson at all, I couldn't believe it. I was one of those people who proposes Higgs theories. But now, of course, LHC has proven me wrong. So these days, whenever I have a chance to go to international conference like this one, I just stand up and apologize, pretending that I'm a proper Japanese. So why there is a scalar boson is still a mysterious question to me. So as I said already, supersymmetry does provide rationale for this because there's just tons of scalar particles in the theory, and Higgs just being one of them. But that particular one tends to get most negative mass squared at the end of the day dynamically, and hence plays the role of being the Higgs in the standard model. Another possible rationale is that the Higgs is composite, just like pion, where constituents have spins, but they cancel among the constituents so that the composite state has no spin at all. So in this case, you have some new strong force, a new layer of the natural world, a new strong attractive force to confine them into bound states. And so that's an interesting direction as well. That's why we always talk about this as another possibility. Maybe the Higgs is spinning in extra dimensions. The string theory predicts extra dimensions anyway. So if the Higgs has a spin, but is actually spinning in extra dimensions, we don't see the spin, and therefore it appears less spin zero particle. So in this case, we can or hope to see the impacts of extra dimensions in the deviation, the Newtonian law, or possible de Kaluza-Klein states. So in all of these cases, they provide rationale why we do have a scalar particle in the theory, and that leads to new predictions and new ideas. And this is a sort of a new naturalness argument, which doesn't rely on this loop level, one loop fine-tuning argument, but nonetheless points to these new physics possibilities just for the purpose of understanding why such a particle exists at all. So we definitely hope for new signals for that. And this is an interesting plot. I actually got it from Alex Pomeroy that the MSSM prefers actually the rather light Higgs. Composite Higgs actually prefers somewhat heavier Higgs. And the experimental discovery came sort of exactly in between those two theories. And so the theories, like myself, have been scratching their head. We don't know which way to go, really. So this is actually kind of frustrating situation indeed. And this is a comment Nemo made at a meeting I attended. So the 125 GeV Higgs seems almost maliciously designed to prolong the agony of the beyond standard model theories, and I tend to agree with them. But for experimentalists, you couldn't have a better mass for the Higgs boson, because if the Higgs was much heavier, like in composite theories, the only thing you could have measured is a coupling to bosons. If Higgs were much lighter, like in MSSM, then the only thing you could have measured are the coupling to fermions. It turns out the 125 is right exactly in between those limits where you have access to all of these couplings in the Higgs branching fractions. So this is actually a dream case. So we hope that we can do very precise measurements of the Higgs properties and learn a lot. And hence, European strategy update last year pointed to the Higgs factory as the highest priority collider in the near future, which of course makes very good sense. And the Higgs also is a very interesting portal to new world like dark sector, because if you think of the standard model in some isolated sector, which I call dark sector for the purpose of this discussion here, and try to write the lowest dimension operator between these two sectors, then whatever operator you write on the dark sector of dimension n can couple the standard model with Higgs with only n+2 power suppression, while the same operator coupled to standard model to gauge bosons and fermions would be suppressed by n+4 powers instead. So it turns out that no matter what dark sector may be, the leading coupling between two sectors is actually through the Higgs boson, and hence the portal. So there is a very likely possibility that once you actually do a very precise study of the Higgs boson knows about this dark sector or whatever other sector that might exist beyond the standard model, and we hope to learn something from that as well. So making sure that we do a very good job in Higgs boson is not just understanding what Higgs boson is, but also understanding what's beyond that at the same time. So one way we can actually parameterize the physics this way, which I already did on previous slide, is to write down effective operators. And so standard model is a renormalizable theory, such that all the operators in standard model dimension 4 and less. And then you can add these non-renormalizable operators suppressed by some higher energy scale lambda, and we can systematically list them up and analyze them. And at the dimension 6 level, there are actually tons of operators, which include things like the proton decay, muon-G minus 2, triple gauge boson vortex. This is OH, which became sort of a well-known in the recent studies. And this is actually an example of the magnetic moment of the gauge boson, for example. So all of these operators appear at dimension 6 level. There are quite a few of them. There's only one operator at dimension 5 level. And in some sense, this is the leading effect of physics at high energies. And this operator is nothing but the mass of the neutrino once you replace the Higgs field by its expectation values. So in some sense, the fact that we have discovered the mass of the neutrino as the first evidence for the physics beyond the standard model kind of makes sense. And so we have learned already something that there is definitely physics beyond the standard model, which is encouraging because that's what we are looking for in the context of also supersymmetry and unification. And looking at the new physics this way, so we'd like to go, of course, beyond the LHC and dark matter experiments, electric dipole moments have indirect sensitivity to much higher energy scales. And of course, the proton decay and neutrino mass probes the very high energy scales. So whatever we can learn from these very rare processes is also very interesting beyond the collider experiments. And unified theories may belong to this kind of energy scale. Just for the purpose of listing up these effective operators, actually used to be a surprisingly difficult question. And Weinberg started this business by writing down first time for the baryon and lepton number dividing operators. Boch, Müller, and Wheeler started writing down dimension 6 operators for the interest in flavor physics point of view. But it turns out that the classification wasn't complete and there was a redundancy among them. And the time when we finally came up with the correct listing of the dimension 6 operators was like 30 years later, Francis Weinberg, and getting correctly for the general number of flavors is actually even more recent. So this actually was not been a solved problem for a long time. And so what I was happy to do is to come up with a general idea how you can classify all these effective operators for whatever particle content you have, including dark sector you like, as long as you specify the particle content and symmetries of that sector. And it turns out that the conformal field theory is a good tool for this purpose, because for any quantum field theories, if you just keep the kinetic terms as the lowest order in the theory, then the theory is automatically conformal, at least in 4 dimensions. So using conformal field theory technique and relying on the fact that there is an operator state correspondence, you can classify operators knowing states, namely the representation theory of CFT. And then in the end, what you have to do is to write the Hilbert series and do the Haar measure integral to obtain the Hilbert series that contains all the effective operators in a given theory. And so at the dimension 6 level, the classification took, as I said, almost 35 years to complete. Now you can do this in a couple of seconds on a computer. Even if you go to dimension 8 levels, there is a large number of operators, but you can do this again on your laptop. It takes a little longer because you have to work out all these characters of the representation theory. And then you have to make sure that you integrate of the Haar measure of all the gauge groups, as well as the conformal group. And that it basically can be rewritten in terms of residual integrals. And so that's what the computer is doing right now. At the end of the day, there comes out the list of all effective operators at dimension 8 level. So this is now automated and you can do this systematically. So if you go to higher mass dimensions, of course, there's an exponential rise in the number of operators. And so at least you know what list you should be looking at. So given that situation, we hope to understand physics at high energies. And of course, LHC is leading the way, trying to probe the energy frontier and has discovered Higgs boson. Now we are getting a little worried. It may be shrouded by this the clouds that we are not quite seeing what's going on at high energies. But at least we have got the Higgs boson, which can be the portal to new world, as I said. So we like to do a very good job in studying it. So it could be BECPC, or I'm hoping that it would be IOC, so that we can do the very good job in doing the study of the Higgs boson. And by going through this effective field theory analysis, we hope to peak at physics at high energy scale. And that's one important role of the EFD analysis of the precision measurements. And also that Higgs itself provides the portal to new world, because we community realize that going to high energy is not the only path for discovering new physics. There's another axis called the coupling. The new physics may be lurking at the relatively low energies, but at small couplings, which may be, for example, the physics that has to do with the dark matter and baryogenesis, for instance. So there is a sort of renewed interest in thinking about the weakly coupled but low energy physics, which can solve these major puzzles along with the supersymmetry at high energies. And so that actually leads to new activities and lots of new ideas for experiments, a lot of new models being written down. And again, this is a very active area of research today. And of course, probing this weakly coupled physics at relatively low energies has been the job of the low energy colliders, for example, the Beijing Collider and the Super KKB running today, and also the beam dump experiment. And hopefully there will be something like SHIP coming in the future, and also constraints from astrophysics and cosmology. So this is the way we used to actually address physics at the relatively low energies, but with very weak couplings. And the facility like IOC can also actually approach this direction, both by the collider mode itself, but also allowing for the beam dump and fixed target experiments along with the collider experiments. So that's one idea I'd like to talk about. And in the end, of course, we really would like to go to high energies by the future upgrades. That's why linear collider is good, because you can just make it longer and go to high energies later on, rather than being limited by the size of the ring in the future. So that's the idea I'm calling IOC++. So it's a comprehensive facility we hope we are going to see in the near future. So having a precision study of the Higgs boson, this could be also done with FCCE and BEPC as well, of course, then you may understand the actual nature of the Higgs boson. Is it a standalone single particle with no context? Or does it have relatives and siblings? That's the idea of supersymmetry, with a characteristic deviation of the couplings. Or it's a composite particle with a different kind of characteristic deviation in the couplings on the Higgs boson. So we will understand the context and the rationale for its existence by doing these precise measurements. And also these effective operators will be measured by 1 order of magnitude better at the high luminosity OHC. And we can go even another order of magnitude better by going to these Higgs factories. And that translates to 1 order of magnitude in energy scale in our reach in sensitivity, understanding physics at high energy scale. So that's the kind of thing we hope to see, so that we will know what is the next energy scale that's important for the higher energy colliders. One direction I've been very excited about is the idea that there is sort of a copy of the standard model relevant for the dark sector, namely that this copy of the standard model accommodates the dark matter, but also at the same time explaining baryon asymmetry. For example, if we have SU2 equals U1 equals SU3 in the dark sector, and if the phase transition of the electroweak in the dark sector is first order, then it can do electroweak baryogenesis in the dark sector, creating both baryon and lepton numbers. But you can connect the lepton number in the dark sector to the standard model just by introducing the right-handed neutrino, that's the neutrino portal. So the lepton asymmetry would now decay to the lepton asymmetry in the standard model, which subsequently get converted to baryon number from the standard model's failure on. On the other hand, the baryon number in the dark sector would undergo QCD phase transition and lead to asymmetric dark matter in the form of, let's say, dark neutrons, or possibility of the dark proton, depending on which one is lighter, of course. So this is the way you can get both the dark matter and the baryon asymmetry. And you do need kinetic mixing between dark photon and our photon to make sure that all the entropy after QCD phase transition in the dark sector gets dumped back to the standard model to avoid an effective constraint in cosmology. But at the same time, because you need Higgs for the phase transition, the Higgs is also coupled to each other with a dimension 4 operator. So at the renormalizable level, you already have a coupling between two sectors. So Higgs knows what new physics is there in a dark sector. So if you actually go through this kind of model, then you can go through the analysis of the direct detection experiments for dark matter, like dark neutron. Then a lot of prominent space gets covered by the near future fixed target experiments, as well as the OHCb. If the dark proton is a dark matter, then the kinetic mixing will lead to the coupling of dark proton on the nuclear target directly. So the future dark matter experiments would have a very good sensitivity on that. In addition, if you have this dark QCD sector together with this kinetic mixing, in principle, you can produce these dark sector resonances or dark resonances using E plus E minus annihilation, where you can tag this visible photon and measure its energy, which is in 1-to-1 corresponding to mass of this invisible sector state. And therefore, just by measuring the energy of the photon, you can perform a spectroscopy of the dark sector. And in principle, you can fit the data to understand the number of colors, number of flavors, the mass of the quarks in the dark sector, just by looking for this E plus E minus monophoton signature. And that will be incredibly interesting. So this is at least a possibility. And that's why looking at relatively low energy E plus E minus machine could be actually very, very valuable at the end of the day, such as Bell 2. And you can also have the situation where asymmetry originates on the standard model side and get transferred to the dark side, leading to, again, asymmetric dark matter. In that case, it turns out that dark neutron, a dark proton, may be as heavy as many tens of GeV rather than the GeV scale as a previous case. So the asymmetric dark matter may not be very light in this case. In that case, you have much weaker constraint from dark photon searches because all the mass scale can be heavier, but many of them can be covered in many different ways, especially by the case of the dark proton dark matter with the future improvements in dark matter detection. And Higgs can also decay into dark sector particles in this kind of scenario. So invisible decay of the Higgs can be improved by order of magnitude at high luminosity OHC, another order of magnitude at the Higgs factories, and even further beyond. So we have actually a orders of magnitude gain in looking for Higgs decay into dark matter. Or in the case I discussed, the Higgs might decay into, for example, dark photons. Dark photon may further decay back into standard model E plus E minus pairs, pi, a jet. So in that case, the Higgs would undergo rather exotic decay modes. And these decay modes can be looked for by 4 orders of magnitude, in some cases, better than high luminosity OHC. So there's plenty of room to go to be probed for this exotic Higgs decay, probing new, light, interesting dark sector physics at the future E plus E minus machines. And having this kind of low energy phase transitions might also lead to gravitational wave signatures at LIGO, Einstein Telescope, LISA, or even using galactic archaeology data from Gaia and Theia in the future. So that's the kind of thing we should look forward to as well. And as I mentioned already, the one advantage of IOC design is that it has a beam dump, and you can mount experiment there. You also have ducts around the IP, so you can put in a forward detector like phaser or surface detect like Matsosa, in addition to the main collider detectors. And it turns out that there's also many beam extraction points in the baseline design. So at some of these extracted points, you can mount extracted beam fixed target experiments looking for dark matter or even nuclear physics. And the people start to look into that kind of possibility. And beam dump experiment looking for dark matter detection can cover actually interesting range of the parameters in a typical freeze out scenarios, or looking for the axion, which decays on the other side. And then you can cover parameter space order of magnitude better than SHIP, for instance. And these things started to be looked at only rather recently, and there's still many things that people should actually look into. So this kind of activity is really welcome, and we are designing a specific conference to really think about what else you can do at the IOC to probe weakly coupled light new physics sector, and that's in a workshop called IOC X standing for experiments in October, and that is going to be fully online, unfortunately. But I really encourage people to sign up and give talks on what new things you can think about by using the electron beams or positron beam, also in beam dump experiments, fixed target experiments, and so on and so forth. But at the end of the day, we do hope that SUSY is somewhere. And John always tell me that it's better late than never. So even if SUSY scale is 10 TeV, it still ameliorates the fine tuning from 10 to minus 36 to 10 to minus 4, which is a lot better. So this may be the right argument in the end. And the advantage of linear design, of course, that we can actually tack on and make the Linux longer in the end. And you can also replace the accelerated technology later in the future to go to a higher gradient. So this way, in the end, the same tunnel where the IOC gets to like 30 TeV, which is comparable in physics reach as a 100 TeV PP machine. So there's plenty of room to go beyond the initial stages. Finally, I'm fixated with this idea that supersymmetry, in addition to be relevant for the theory of the natural world, but can also be a theoretical tool to understand the gauge theories. And one application I came up with lately is to understand QCD, because I know I still had this uneasy feeling about QCD for a long time since the graduate school, because what you get told in the graduate school is that, look, here's a proton, but they are actually quarks inside. And those three quarks are very colorful and beautiful, but you can never see them. You can never take them out. And it sounds like internet scam, right? So this is very unsatisfactory. Of course, you learn, or you get told that this is a property of QCD called confinement. Now, there's a technical term, sounds more serious, but you still don't understand that. We, of course, know in our beautifully demonstrated experimental data that the QCD coupling constant is asymptotically free. It grows and becomes strongly coupled at low energies. But going strong coupling only means that you can apply perturbation theory. It doesn't prove confinement either. So it's only suggestive. At the same time, we also need pion to be much lighter than proton. Otherwise, the nuclear binding force, as predicted by Yukawa, doesn't go beyond the size of the protons and neutrons, and the nuclear wouldn't bind. Then the only atom there is in the universe is hydrogen. The rest of the periodic table would disappear in that case. So for us to exist, it's very important that pion is much lighter than proton and other hadrons. They are still made of the same stuff, but there is a big mass difference. And of course, we get told that it's due to chiral symmetry breaking. And if you believe that, then you can understand why pion is light, but you don't know how to show chiral symmetry breaking from the QCD. So these things are still rather unsatisfactory. That's why I still feel like the whole thing is an internet scam. And here's an example I still had in my inbox. But it starts to feel a lot better recently because the Seiberg and Witten could demonstrate that there is a confinement in an N=2 supersymmetric Young Mills. And this theory has a Coulomb branch described by the moduli space using the coordinate U, which is the gauge invariant out of this adjoint scalar field. And on the Coulomb branch, there are two singularities they demonstrated where the monopoles or dion can become massless. And upon perturbation to N=1 by introducing the mass term for this adjoint fermion, then you can show the monopole indeed does condense. And therefore, that will lead to the flux tube of the electric field. And then the electric field would behave with a linear potential. Therefore, there's a confinement. So this was actually a very good advancement. So now at least we know how confinement might happen in the form of monopole condensation, thanks to supersymmetry as a theoretical tool. But what about chiral symmetry breaking? Well, N=2 theory actually doesn't have chiral symmetry because of the superpotential breaks chiral symmetry to the vectorial symmetry. So you can talk about spontaneous breaking of chiral symmetry because it's already explicitly broken. On the other hand, Seiberg told us that N=1 theory can be solved, but it has two unusual phases which don't resemble non-supersymmetric theories at all. But it turns out that if you actually specifically break N=1 theory with anomaly-mediated supersymmetry breaking, you can work out its consequence even on composite states like mesons and baryons, thanks to the sensitivity property called UV insensitivity of anomaly mediation. And you can work out the exact results for the non-supersymmetric theory starting with N=1. And an N=1 theory, as Seiberg told us, has these weird phases which doesn't resemble the non-supersymmetric theories at all. But in addition to these ideal fixed points, we know very little about non-CG theories. The only thing we know is basically the Banks-Sachs fixed point towards the edge of asymptotic freedom. In the case of rather few number of flavors where we believe chiral symmetry breaking, largely based on experimental data, but now also based on the lattice calculation. But in between, we know rather little. It turns out that when you actually introduce anomaly-mediated supersymmetry breaking of infinitesimal value, then all of these weird phases collapse to the standard chiral symmetry breaking as expected in non-supersymmetric QCD. I still don't have exact results in this conformal window. I'm still working on that, but it does look like this chiral symmetry breaking is smoothly connected to what we expect in non-supersymmetric theories, and that was a very satisfactory result. The way it works is that when number of flavor is small, we have this Lafelec-Dine-Seiberg potential. But if you include anomaly mediation, you can show the potential has a minimum, and the minimum does have the correct form of the chiral symmetry breaking. And the Messino, the super partner, acquires small mass due to SUSY breaking. And Messino saturates all the anomalies. So by integrating that out, you also generate correctly Wessel-Witten term, the chiral Lagrangian, and so on and so forth. And for a larger number of flavors, you again can show and minimize the potential and obtain the exact result, which does demonstrate the chiral symmetry breaking. So in addition to all these reasons we talked about why SUSY might be great, there's also another way of making supersymmetry great, because it's a great tool to understand field theory. Even in the case of chiral gauge theories, you can apply the same technique. So as a result, I'm still interested in supersymmetry. We don't know when it gets discovered, but maybe in like year 2040, and you might see the headline in newspapers, the other half of the universe discovered, namely superpartners. And then the SUSY conference in those years will be really exciting. And we just learned that next SUSY conference will be in Greece, but for this exciting SUSY conference, I hope the candidate site will be somewhere around there. Thank you for your attention.
Thank you very much, Hitoshi. Very beautiful talk. Heuristic, enlightening, comprehensive. Yeah, we still have time. Any questions to Hitoshi?
Hello?
Yeah,
Hello, can you hear me? Yeah. In your talk, you showed there are some motivation for supersymmetry. One particular reason I want to ask is it helps us to stabilize this inflaton potential. Can you talk more about this?
Yeah, so what I mean is simply that the inflaton potential, it has to be written in supergravity, of course, when you actually combine inflation and supersymmetry. And the getting the flat potential at the tree level is actually not easy. So people try to come up with all kinds of different ways of justifying flat potential. But if the inflaton has other interactions, then you expect the radius correction on top of that, and that may screw up the flatness of the potential once again, even if start with the tree level flatness. And that's where the supersymmetry at least helps to regulate this radiative corrections to maintain the flatness, including radiative corrections. So it doesn't always work that way, but at least it's a great help in terms of getting the consistent theory of inflation that way. So that's what I meant.
Okay, thank you.
Any further questions?
Okay, I have a question.
Yes.
Okay,
Yes,
can you hear? Yeah. I wonder what your solution to the chiral symmetry broken. I wonder what's the SUSY broken scale? Is it high
I'm sorry.
or low? Then what's the SUSY broken scale in your solution? I wonder what's the SUSY broken scale in your solution to the chiral symmetry broken by combine MSB.
So in this case, I'm using that just a pure theoretical tool. So what I can do is that when supersymmetry breaking scale is much smaller compared to dynamic scale of the supersymmetric QCD, then you can extend Seiberg result and obtain the exact result on the ground state. So as long as SUSY breaking scale much smaller than lambda, you can solve it exactly. I lose theoretical control when I push SUSY breaking scale beyond lambda. But if I assume that there's no phase transition, then it would stay in the same universality class, and therefore same massless particle content and same symmetry breaking pattern. So that's what I'm hoping. Does that answer your question?
Okay, thanks.
Okay.
Further more questions? If no others, Hitoshi, may I ask you a question? Just yeah, very briefly. What you said you have this is your second time doing the summary talk in the SUSY conference. May I ask you briefly outline what is the difference of you?
I'm sorry.
You put out.
I couldn't hear your question.
Breakthrough, the development of the SUSY in these years.
Development of supersymmetry in this year as opposed to the previous years?
Yeah, just the difference between your two summaries. Yeah, that means the development of the SUSY in these years.
Yeah. So I think the main difference from 5 years ago is that this direction of thinking about relatively light, but nonetheless weakly coupled new interesting physics has really blossomed in the past years. And that also led to very active research going on in coming up with experimental approaches to them, and including the new dark matter detection techniques and also the kind of beam dump fixed target experiments I briefly mentioned. So all of these things are relatively new activities that we didn't have much 5 years ago.
Oh.
So that's on the phenomenological side, I think that's the major development. And for myself, this using supersymmetry to understand dynamics of gauge theory is also something I started only back in April. And that's a new development as well. And I'm very excited about that. Of course, I'm biased.
Thank you. Yeah. Is there any further question? Okay, if not the case, let's thank Professor Murayama and
thank you for your attention.
All the contributors of this great SUSY meeting this year.
Yeah, and also I'd like to thank all the organizers who made this conference possible, despite this hardship of being fully online. So let them give a round of applause.
Yes, yeah. The very last, the man of the chief organizer, Professor Tianjun Li from CAS, will give some final remarks. Please, Tianjun.
Okay, so just give me a second, so I share the screen. So can you see my screen?
Yes.
Okay, so I will start. So on behalf of the organizing committee, it's my great pleasure to present the acknowledgements for SUSY 2021 conference. Our sponsors are Chinese Academy of Sciences, CAS, National Natural Science Foundation of China, NSFC, Institute of Theoretical Physics, ITP, CAS, University of CAS, UCAS, Institute of High Energy Physics, IHAP, CAS, China Center of Advanced Science and Technology, CCAST, International Center for Theoretical Physics, Asia Pacific, ICTP-AP, Peking University, Sichuan University, Tsinghua University, as well as the journals such as Communications in Theoretical Physics and Symmetry. So logos are given here. So first, I would like to thank my colleagues at ITP-CS, our director, Ronggen, our particle physics group, Zhao Xi, Chao Sang, Yu Qi, Chun, Jianping, just give me 1 second here. Jin Min, Jiang Hao, Yu Feng. Our research department, Xiao, Wei, Xin, and Zi. Our accounting department, Wei Yue, Yi Jun. Our information department, Yi Bo, Bin Bin, Zhi Lin, and Zi for their support and kind help. I would also like to thank the International Advisory Committee, Ignatius, Shapa, Wim, Marcela, Miriam, St. Ignatius, Keith, Herbert, Baska, John, Jonathan, Jen, Mola Ranjan, John, Kauru, Tao, Gordon, Dimitri, Ivan, Paul, Joseph, Maria, Robindra, Pran, Apostolos, Fernando, Mariana, Graham, and Barbara. In particular, thank Pran and Tao for their suggestions and advices. Also thank Baska, Barbara, as well as Babu for telling me how to organize the SUSY conference in details. I would like to thank program committee, Tao, Yang, Robin, Stephanie, Rooney, Xiaogang, Chun, Mihoku, Sylvia, Jianmin, Harry, David, Su Fang, Lian Tao, Susan, Su Tomu, and Jim Min. Yeah, for selecting the plenary speaker and the conveners. So next, I would like to thank all the conveners. 连涛、金明、旭爱、Norsin, Babu, Ilya, Nobuchika, Fei, Dan, Masahito, Eugene, Robin, 招风、苏芳、俊杰、Alexander, 建明、Eleni, Lorenzo, Yin, Emmanuel, Robert, Paul, Claudia, Annie, 郑华, Michelle, Baska, Edna, Newpan, 海鹏、杨、Stephanie, P. Wang, 文宇、云贵、Sugumi, Germano, 安宗、Giacomo, 易安、Alexi, Andre, Bin, Babak, Sven, Gary, 海棠、雨婷、杨、Jacob, Shaba, Nishita, 金冕、Gosia, 宇、Christopher, 柯晨、Peter, Nick, 乔丽、玉孝、洪、建新、纯、Kiss, Shaba, and James for their invitations to the parallel speakers, arranging the parallel programs and chairing the parallel sessions. I would like to thank the experimental collaborations, Atlas, CMS, LGCB, Bell, Bell2, IceCube, Fermi, Muon-G-2, and Dual collaborations for selecting the plenary speakers and the parallel speakers. Here, I would like to thank the local organizing committee, which is big. So we have Jinmin, Haipeng, Xiaojun, Lorenzo, Junjie, Qinghong, Wei, Bin, Shaolong, Edna, Bo, Taifu, Jun, Xin, Yu, Yungui, Jun, Babak, Hongjian, Nick, Yanping, Zaofeng, Chongsheng, Jinmian, Miao, Su, 文君、银、伟、义、纯、国立、玉孝、严东、左伟、财典、洪、建新、波、强、建平、义友、家树、崇峰、金、中国、曾、义磊、分、柯晨、磊、彭、清、文宇、小川、磊、裴文、小红、新刚、志荣、志忠、丹、训、启树、文斌、海棠、乔丽、硕、亚东、江浩、崇新、洪浩、树敏、郑华、宇峰、斌、金亚、守华 and Xi, especially Chen and Jimin organizing the SUSY2021 conference, and in particular, they promised to provide the financial support if the conference was held in person at the China National Convention Center, which is very expensive. So I would also like to thank Yu and Wenyu for preparing the SUSY 2020 proposal. And thank Xi for creating the Indica website for SUSY 2021 and pre-SUSY 2021. I would also like to thank Jinmian, Bingwei, Zhen, Jun, Peng, Haitang at Sichuan University, who organized a wonderful workshop in June 2019 with an evening meeting to prepare and propose a concrete plan for the SUSY 2021 organization. And in my opinion, this is the most important meeting for our organizations. In particular, I would also like to thank the website and email group, Lorenzo, Xin, Nick, Zaofeng, Jinmian, and Zhen, for building the websites, sending the invitations, replying all the emails, arranging the whole programs, and being backup chairs. Next, I would like to thank our room host group. In particular, I would like to thank Yu Gao, Yu, Chen Chen, Jinmian, Zhen, Jun, Fei, Haitang, and Bin for creating a Zoom room host group And this group contains Jun Song, Yi He, Xiao Kang, Han Wen, Lin Qing, Zhan, Ao Yun, Yu Chen, Min Xia, Li Jun, Xin, Hai Jun, Fei Fu, Jin Ji Yang, Jun Le, Wang, Mudasa, Rui, Jia Yi, Lina, Qi, Ya Dong, Fei Yu, Xiang Wei, Lin Kai, Xin, Ying Kai, Chi, and Wen Xin. So I would like to thank all of them for their hard work during last 5.5 days. And last but not least, I would like to thank all the plenary speakers, all the panel speakers, and all the chairs, as well as all the participants. So looking forward to seeing you all at the SUSY 2022 in Greece. Thank you all very much for your attention and have a wonderful weekend.
Okay, the party is going to the end. See you all in Greece in person next year. Bye-bye.
Okay, bye-bye.
Bye.
Bye, everybody. Thank you.